So now that we've analyzed the algorithmic decomposition of our expression tree processing app, we're finally in a good position to evaluate the object-oriented and pattern-oriented design of the expression tree processing app to see what it does better than the other approach we just looked at. So we're going to take a look at the pros and cons of the object-oriented and pattern-oriented approach relative to the algorithmic decomposition that we just looked at. So one of the key things that the algorithmic approach didn't do was model the application domain very well. In contrast, that's what the pattern and object-oriented approach does very well. So what you can see here is on the left-hand side, we see sort of the domain of expression trees with binary nodes and unary nodes and leaf nodes. And on the right-hand side of your screen, you can see our pattern and object-oriented design, which uses inheritance and hierarchical data modeling in conjunction with the composite pattern in order to be able to have different levels of abstraction handling the different types of nodes. So you can see that we've got binary nodes represented by this subclass called composite binary node. We have unary nodes represented by this subclass called composite unary node. We've got leaf nodes represented by the leaf node subclass. All of those inherit either directly or indirectly from the component node root of the hierarchy. And then we further customize these classes by having composite add nodes, and composite negate nodes, and so on and so forth. So that's all very clean and elegant, and of course, pattern-oriented. We also get more effective encapsulation. So by using the bridge pattern, we're able to hide from clients even the details of our wonderful composite data structure. So we can have different ways to represent the composite, but that's all nicely encapsulated and hidden behind the abstraction class from the bridge pattern. And that way the client doesn't have to be aware of any of the tree node implementation details. In contrast, the algorithmic decomposition exported all those fields as first-class entities in the type system of the expression tree, and it was very brittle and error-prone. As a result of doing these things, the object-oriented and pattern-oriented approach is much, much more straightforward to extend. So if you want to add new types of nodes, if you want to make a mod node for a modulus, or even if you want to come along and do a ternary node, all those kinds of things are cleanly and clearly handled by simply defining new inheritance relationships and leveraging and extending what's already been designed in the previous object-oriented hierarchy. But of course, everything's not perfect, even with the object-oriented approach. And so one of the consequences of the object-oriented approach is that the solution can be overly rich in classes and associated structures. So if you take a look at the design of this, you'll see, wow, there's like a dozen different classes, and that can be daunting at first. So the key to making sense out of this is two things. First, if you're going to have this many classes, you really need to have good configuration management and good use of modern techniques like DevOps and test-driven development and ways of dealing with configuration and rollout and continuous integration and so on. So that's one piece of the puzzle. The other piece of the puzzle, of course, which is really the key point of this whole course, is knowledge of patterns. So once you recognize that all these classes are not just sitting out there trying to drown you in an ocean of complexity, you quickly realize that some of the classes are dealing with the builder portion and the builder pattern. Other classes are partaking in the composite pattern. Other classes are partaking in the bridge pattern or the interpreter pattern or the factory method pattern or the state pattern. It goes on. And the point is that once you see the patterns, then you can look at your design from a higher level of abstraction and not get caught up in all the low-level details. There's also always the niggling question of whether or not you have to worry about extra overhead due to virtual method dispatching. And of course, this is one of those things where modern C++ compilers can make these problems just disappear altogether. So good compilers that we have like G++ or Clang, LLVM, they do a wonderful job of devirtualizing calls wherever possible, of optimizing calls, of using techniques like adjuster thunks and so on, in order to be able to make virtual method dispatching or virtual function dispatching just as efficient as a long if-else chain or a switch statement. So that the good news is that these are no longer really problems in practice. So to wrap up this whole discussion about comparing and contrasting algorithmic decomposition with object-oriented and pattern-oriented approaches, object-oriented and pattern-oriented designs are characterized by structuring the software architecture around objects and classes within a certain domain, of course, like we see here where we've got iterator and visitor and composite and strategy and bridge and factory method, all these good things, rather than decomposing the software around the actions they perform. So we don't decompose it in terms of the steps. We don't do top-down refinement. We don't write switch statements very much, if at all. We don't have large if-else chains, much, if at all. And as a result, the system becomes much easier to understand, extend, and improve over time. Why is that the case? Because inevitably systems evolve, functionality changes, there'll be new requirements, there'll be new environments. But if you do a good job of scope, commonality, and variability analysis and define your objects and classes in a clean and cohesive way, then these relationships are actually relatively stable over time. So therefore, it's always good, I think, even in today's world where more and more languages are leveraging generic programming or functional programming, which is inherently algorithmic, to think about structuring the architecture and the design of your software using objects and classes rather than using actions and functions. Functions and generic program capabilities like STL algorithms, those are great, but they shouldn't be the design of your software. They should be the thing that are doing the computations in the context of a well-defined object-oriented and pattern-oriented design. And to learn more about some of these concepts, I recommend you take a look at the SOLID principles, which was popularized by Robert Martin and his colleagues. And they have a lot of good insights about things like the open-close principle and the Liskov substitution principle and other types of capabilities that are very useful for building software that's designed to grow and expand over time. Naturally, knowledge of patterns from a design point of view and frameworks from a detailed design and implementation point of view are essential in order to understand and document and be able to implement the key roles and responsibilities in complex software systems. And as we've seen before, these patterns really help to hold all the pieces together in the architecture so it becomes easier for humans to make sense of them and to improve them and evolve them and enhance them.